Hello and welcome to the first video of the third topic, as I've labelled it, of the Year 11 Methods course. We're moving into arithmetic and geometric sequences and series, and this is the first video on arithmetic sequences and series. So in terms of the unit overview of what we're going to be covering in this video, we'll be having a look at the recursive definition of what a arithmetic sequence looks like, and how to define an arithmetic sequence in that sense. We'll also then be looking at the general term of an arithmetic sequence. We'll also be having a look at contextual applications of arithmetic sequences, how they appear in real life, and this is often takes the form of worded problems in your tests and exams. And we'll also be able to determine the equation for an arithmetic series as well. And this last term, yes, the sum of the first n terms of an arithmetic sequence, that's referred to as an arithmetic series, and we'll be looking at the formula for that. So let's get straight into it. Okay, so the first thing I want to do is I want to define what an arithmetic sequence actually is. What an arithmetic sequence can best be approximated by is kind of a linear relationship between y and x. That is, you're going to have an initial value. Let's call that value a, and this value will have some sort of value, let's say 1 for example, and then it'll increase by a constant d. So let's say that d is 3. And so this arithmetic sequence would define something that looks like 1, then 4, then 7, then 10, then 13, then 16, and so on and so forth until infinity. We can define this arithmetic sequence in terms of a recursive rule. So that's the recursive definition here of an arithmetic sequence. And what we mean when we talk about a recursive rule is that we are defining a term in terms of the term that precedes it. So for example, 13 can be defined as 10 plus 3, 16 can be defined as 13 plus 3, 7 can be defined as 4 plus 3, and so on and so forth. That is, the t(n plus 1th) term is equal to the t(n)th term plus the difference d. And so in this case we have our t(n plus 1th) term defined as tn plus 3. And now the important thing is that in order to determine what tn plus 1 or tn is in the first place, the way we need to define this is by having a t0 term, which is equal to a in this case, and this a value is in this case equal to 1. And so in this case our t0 term equals 1, our t1 term equals 4, our t2 term equals 7, and so on and so forth. We can also label this as our t1 term if we really want to. And so in this case we can define t1 as 1, t2 as 4, t3 as 7, and so on and so forth. So I think in terms of like what your subscript is here, it really depends on whether you define your first term as t0 or t1. And you can see both cases in your tests and exams. Okay, so that's the recursive definition knocked out. We can also have a look at defining the general term for an arithmetic sequence. And in this case specifically, we use, we have our tn term. We define it in terms of our first term, and then the sum of all the d terms that demarcated each of the previous terms. So if we have 10, for example, here, we can define that as 1 plus 3 plus 3 plus 3, or 10 equals 1 plus 3 times 3. It should be noted here that 10 is our t4 term, and this being our value n. And so in terms of defining what our t4 equals 10 term is, we're defining that as our difference a is 1 times plus n is 4, n minus 1 is 3, n minus 1 times our difference d. And so this is us representing 10 as our 10 as our general term in terms of our initial term a and our difference d. It should be noted as well that if we define our arithmetic sequence in terms of t0, then t1, and so on and so forth, then in that case we would write our general term tn as a plus nd, because in this case our 10, the 10 here is actually our t3 term. Okay, because we initially had t0, and in this case our n is equal to 0. So in this case, t0 equals a. t1 in this case equals a plus 1 times d equals a plus d, and so on and so forth. So this is why if we define our first term as t0 or t1 matters. It affects how we express our general formula for an arithmetic sequence. So in terms of representing our arithmetic sequence in a worded problem, or instances where we can see arithmetic sequences in worded problem in real life scenarios, is generally where we have a constant increase in, for example, production, or let's say we add money and we're not considering interest. Okay, so for example, you might have a machine that on the first day produces 1 product, on the second day it produces 5 products, on the third day it produces 9 products, and so on and so forth. And we want to determine what the recursive and the general term formula for this arithmetic sequence is. So the thing that we can see is that our a value is going to be equal to 1. So the first value of our arithmetic sequence is 1. On the first day we produce 1 unit. On the second day we produce 5, and then 9, and so on and so forth. So here we can see that our difference is equal to 4. And so if we wanted to define our recursive rule, we could define that as tn plus 1 equals tn plus our difference is 4. And we should note as well that our initial term, t1, is equal to 1. We can also write that as a equals to 1 if we want to. We could also write this as tn equals tn minus 1 plus 4 if we want to. The important thing is that this term is 1 less than this term in the sequence. In terms of the general formula, we can define any term in our sequence tn as equal to a, 1, plus n minus 1 times our difference d, so 4 n minus 1. And this hinges on the fact that our first term, in this case here, the 1, is defined as t1. Okay? Alright, so this is an example of a context where you might use an arithmetic progression or an arithmetic sequence. I'm using sequence and progression interchangeably in this case. Now let's move on to the series. Definition of a series. So what a series is it is the sum of an arithmetic sequence or an arithmetic progression. So if we take the example that we had initially, 1, 4, 7, 10, 13, and so on and so forth, up to some specific value, let's call it the x term of the sequence, the x term, we can write our series is defined, if this is our arithmetic progression here, so this is an arithmetic sequence or an arithmetic progression, so progression slash sequence, we can define the arithmetic series that corresponds to the sequence as 1 plus 4 plus 7 plus 10 plus 13 plus so on and so forth up to whatever we call it, x. Okay? Well, if we want to define x more generally, we can write that as a plus 1 plus 3n minus 1, where n is the nth term of that sequence. Corresponds to the nth term of that sequence. So this last value corresponds to the nth term of the sequence. So this is what we define as the arithmetic series that corresponds to that arithmetic sequence or progression. Okay? If we want to define what the formula for an arithmetic for the arithmetic series is we can define a series, a sum of all the values as a plus d plus a plus 2d plus so on and so forth, until we eventually reach a plus n minus 1 times d. And we can equally write this, if we write that as s1 and that is s2, or let's say we can write this as sum of n terms. We can equally write this in the reverse order, so a plus n minus 1 d plus a plus n minus 2 d plus so on and so forth, till eventually we reach a plus d plus a. And if we sum these two values together and we add those together, we can reach 2Sn, and that Sn value will be equal to summing these two values here. So what these two values are equal to is 2a plus n minus 1 times d, and then we sum the next two values together. And in this case, those two values will equally be equal to 2a plus d plus n minus 2 d, which really that can be written as n minus 1d. And then we can do that so on and so forth. And then we have 2a plus n minus 1 times d. And so we essentially have 2a plus n minus 1d, and this term has been repeated n times. Okay, and so we can write this as n times 2a plus n minus 1d. And this is equal to 2Sn, so the sum of our series Sn is equal to n over 2 multiplied by 2a plus n minus 1 times d. And so that's the formula for n terms of an arithmetic series. A really common example of an arithmetic series is the triangular series, where you essentially have a difference 1 plus 4 plus 5 plus n. And essentially the way that we define the sum of this arithmetic series is something that Gauss was able to figure out, and that was equal to n times n plus 1 over 2, and n being the number of terms in this arithmetic series. But if we substitute this value into our generalized arithmetic sequence formula, we can see that we'll get the exact same value. In this case, our n value is equal to n, of course, our a is equal to 1, our d is also equal to 1, and so if we substitute those values into the generalized arithmetic series formula, we get Sn equals n over 2 multiplied by 2 times 1 plus n minus 1 times 1, which in this case is equal to n over 2, 2 plus n minus 1 is equal to n times n plus 1 over 2. And so we have the equation, or the formula for the triangular series, the triangular numbers series, which Gauss was able to determine. This, in this case, however, is the generalized form of an arithmetic series to determine the sum. So, in this video, we went over the recursive definition of an arithmetic sequence as being Tn plus 1 equals Tn plus d. We can equally write that as Tn equals Tn minus 1 plus d, and so on and so forth, however we want to determine it, as long as this value is 1 greater than this value. We then were able to look at the general formula for the general term of an arithmetic sequence, and we could see that because it was increasing by a constant each time, it could be best, it has a linear nature. We then also had a look at contexts of linear growth and decay, such as this case of the machine production, and in fact it can also be used to approximate simple interest as well, because you always have a constant increase in however much interest is being gained. And then finally we also had a look at the definition of an arithmetic series, and this is this point 2.4. This is referred to as an arithmetic series because it refers to the sum of each of the terms in the arithmetic progression or the arithmetic sequence. And so that is arithmetic sequences and series done. So I just wanted to thank you guys for watching this one. remind you to comment if you have any questions regarding any of the content here. If you've come across any difficult questions that you're not able to solve, I can also go over those in the supplementary content, because these can get a little bit more tricky than I've shown already. Also wanted to mention that you should subscribe so you don't miss any of the new videos, and I'll be uploading my video on geometric sequences and series, which will complete this topic on the 12th of November, so in 3 days. Thank you for watching this, and I'll see you in the next one.